Ladies and gentlemen, welcome to my talk on some of the safety issues that I believe exist in gPTP as defined in IEEE 802.1as. And I also want to give you a little bit of an idea of how I propose a potential solution. In case we have not personally, and you have not seen me before in one of the other talks, here's a little picture, and I'm looking forward to see you later on in the question and answer session. So let's go into a little bit of detail on how 802.1as describes the gPTP system and the time-aware systems involved therein. I have recreated the drawings that you can find in the standard, and I have split these apart into the master clock, where basically you have a clock source and a clock master that send out the timing information that is decisive for the whole system. Then I'm showing a time-aware bridge here, and we have to talk about that bridge in a little bit more detail. And then I've shown a time client where we see the clock slave and the actual clock target where time is used. I want to introduce you to a little bit of my symbols and nomenclature that I am using in this talk. The first most important one is the synchronized time, the time that the grandmaster propagates through the system and keeps updated and wants to synchronize with every node. You can see that all of my time-aware nodes in here show this synchronized clock. Keep in mind that this is not necessarily a requirement for a bridge. If you have a transparent bridge, then this synchronized clock in the bridge is actually not required, but we will see that if you follow the proposed solution that I'm presenting here, then you will need a synchronized clock within the bridge. The other clock that is important is obviously the local clock, the free running clock that you see on the bottom. I have only shown those for the time-aware bridge and for the time client, as I am assuming that the master has no requirement to have such a local clock. Having this local clock is a very important element in the two-step process of time synchronization, as it allows us to start the system and actually do some measurements before we actually receive the actual synchronized time from the grandmaster instance. You see the little guy down there that's looking at his watch. That is sort of the time stamping process that I want to express. And obviously this time stamping process happens at event messages. And this is usually done with the local clock, and we need to discuss whether that is the best idea that we can have. What is the problem that we're trying to solve in this talk? The problem description is as follows. As you know, if you've read anything about gPTP or PTP of 1588, then you know this is very much a one-way protocol. The grandmaster sends out sync messages. These sync messages are forwarded by time-aware bridges to either other bridges or other time-aware clients, and all link partners perform pDelay measurements on the local link, but effectively there is no feedback from the clients or from the bridges to anybody outside to say whether this synchronization process has actually worked correctly or whether there has been a problem. So the problem that we're trying to solve is we want to make sure that the grandmaster and specifically the time clients on the right actually all have the same synchronized time at some point of real time that we define, we want to make sure these are all showing the same synchronized time as we proceed and as the system runs. If I told you what the problem description is, I better tell you what I'm not looking at. I am not looking at what you might want to call synchronization accuracy. I do not want to check whether these 3 clocks that you saw on the previous slide actually show real seconds as you might define by the International Atomic Time Standard. All I'm looking for is, do they run synchronously and synchronously? But this is a system intrinsic synchronicity and not a synchronicity to, for example, the universal time zone. I'm also not looking for any checks on does the system have the correct date, like something that you might want to have for security. This is not the goal of this solution. Again, the goal is only to keep everything in sync at a local level and agree upon all nodes that they do show the same synchronized time. One of the biggest problems in this endeavor is actually what has been called a Byzantine error in a bridge. What we have depicted here is a grandmaster sync follow-up message coming in from the left, and this time-aware bridge forwarding this time with a sync and follow-up message to the right at a later point R2 in time. Now, if this bridge adds a term delta error to what it sends out at time R2 in comparison to how the actual grandmaster synchronized clock would have proceeded, as you see on the left-hand side, then the clients or the bridges on the right-hand side live in a time zone, so to speak, that is off by delta error. And you might argue that such a hump, such a jump in the time can easily be detected. And that is quite true, but it is only true if that jump occurs during operation. It is not true if this difference, delta error, is present from the very beginning of the startup of the system. So let's have a look at some solutions that have been proposed. And I want to start with the statistical approach, where basically we assume that an event is happening over on the right-hand side in some more or less cyclic fashion, and then the result of that is transported to a receiver, including a timestamp of when the event has actually happened. And now we can actually check for the statistics of these arrival times and the timestamps. And if we roughly know what we want to allow for delay in the network and what overall accuracy is, then we can probably check whether the client is looking at the same clock as we do in the receiver. But again, there is a chance for a constant delta error offset. If that offset is just small enough in comparison to the accuracy and the network delay, we have no way of detecting this offset if it occurs from the beginning of the system startup. Another solution I often run into, proposed solution that is a redundant grandmaster. We use 2 grandmaster clocks and we distribute both clocks in 2 different domains as is allowed with the new IEEE 802.1 standard. We distribute both time domains to the different clients. And then we have at each client 2 time informations, and we can compare those and see whether those are equal and thereby hopefully detect an error. Well, that is generally true, but it's only true if we can make sure that from the beginning we actually synchronize our 2 grandmasters. If these are not synchronized from the beginning, then our system doesn't start up. So I believe by adding an additional grandmaster, we have added, if we assume the same reliability for all elements, we have added another element, and therefore we might have accidentally reduced the availability of this overall system. Depending on how you do timestamping in the time-aware bridges in the middle, one of these bridges could have a common cause failure for both paths of the time distribution. And so time client B, for example, to the right, might still be living delta error in the past or in the future because one of these bridges has made, time-aware bridge 2 has made the mistake on both domains, and therefore time client B has no way of telling this apart. Furthermore, the question is, of course, what do the clients do? Who do they notify if these two clocks misalign? And what is the consequence of a misalignment either during startup because they're not synchronized? There is all kinds of additional error cases that are introduced by having two grandmasters. A little bit of those problems can be avoided, as obviously we can deliver the time via two different interfaces from the two grandmasters. That obviously adds even more additional elements to the overall system, and thereby my concern is that, again, we might actually reduce the availability of the system if we assume a certain reliability for all of those components. Technically, in here, when the bridges do introduce the constant offset to a domain, then time client A might see a wrong time from bridge 3, and time client C might also receive a wrong time from time-aware bridge C. And therefore, we have this problem that looking at two clocks, we don't know which one is correct, and we don't know where the error actually occurred. So I wanted to present to you what I call the central validator approach. And this has local aspects and it has central aspects in checking for the correct time. Let's go on to one of the local aspects and let's see what we can do when multiple sync follow-up message pairs arrive at a time-aware system. What you see here is that a time-aware system has synchronized its its synchronized clock, its clock slave to the master that is over to the left. It has used sync and follow-up message that have been received previously. And what we can do from a certain point in time is we can actually predict what we expect to see in a follow-up message once we have seen a sync message. What we need to do is we need to associate for each timestamp that we take in local time on this sync event message, we need to associate that with a timestamp of our synchronized time. And we need to do it before we actually use the new information in the follow-up message to update our synchronized clock. And thereby we can detect whether there have been unexpectedly huge differences from the clock that is coming in from the master, or if our own forwarding inside the machine has caused some jumps, we would also see that they differ between what we see in the follow-up message and what we predicted from the local timestamp that we took when the sync message came in. So these are two timing items that we want to hang on to: the time when the sync message came in and what we actually predicted it to be and what the actual follow-up message was. Furthermore, we can do a similar thing for the pDelay messages. we can, for the pDelay messages, not just use the local time, but also record on both sides the synchronized time of when a pDelay request was sent, when a pDelay request was received, when the pDelay response was transmitted, and when the pDelay response was received. Now, in order to actually do a good comparison between the two synchronized clocks, it'd be very advantageous if all 4 synchronized timestamps would be available on one side. And initially, in this concept, one idea was to actually do the pDelay follow-up not in local time, as is currently the idea in the standard, but to actually do this in synchronized time. But as my friend Carl Budweiser pointed out, that's actually not really a good idea. The point being that if you do pDelays in local clock, what you basically get is the rate correction. You can do the neighbor-rate-ratio calculations, and as links start up, you can actually add up or actually multiply these neighbor-rate ratios. And once you finally get a message from the grandmaster, you have the rate ratio to the grandmaster basically already available from the pDelay messages in local time. And so once you actually receive a sync follow-up pair, you can immediately synchronize your clock, and it will hopefully already be synchronized due to having started up the pDelay process before. Now, this requires, as I said before, a boundary clock on our time-aware bridges, as we need that synchronized clock to do predictions inside the bridge and actually have the same process going in client and bridge slave ports. Summarizing what we're collecting in terms of data leads us to this table. This is 12 timestamps in total that we want to be looking at and that we want to collect for every link. This is basically the local clock of a master port that has sent out the sync message. The precise origin timestamp, lowercase t master, that is communicated in the follow-up message from that master port. And then on the receive timestamp side, we want to have the client local timestamp, capital T client, when this sync message was received. And we want the predicted synchronized time when this time was received, and we want to compare that to the content that is coming along in the follow-up message. On the pDelay request message, we have the same pair. We have the local timestamp and the equivalent synchronized time when the pDelay request message was sent. And then we receive this pDelay request message on the other side. We record the local timestamp because we need that for the follow-up message and for the whole pDelay process. But we also associate this with the synchronized time at exactly that point in time when the pDelay request message was received. Same thing for the pDelay response message, where we record again in local time when it was transmitted, and we associate again the time in synchronized time when it was transmitted on the responder. And on the other side, we again record the local time, which is what we need for the pDelay process again, and we record the synchronized time that we associate with this reception point in time. In AutoSAR, there have been interfaces added to get these times, and I think it'd be really nice if we could include similar interfaces to read these time tuples in 1AS and in 1588 as well. But as I mentioned before, this requires the synchronized time to be available on all slave ports and on all master systems. So we are requiring boundary clocks with the system. Now, what do we do with this set of 12 timing information elements from our system? And why is it a good idea to record these? Let's look at a mixed system where we have a grandmaster, we have some time clients that are safety relevant, and we have other time clients that are not safety relevant. And we have a lot of bridges that might have very general implementations and therefore would not want to go to a safety relevant implementation. Keep in mind that a safe client, as shown to the right, needs to make sure that any clock target actually receives the clock slave time without any of these delta errors that we discussed in the bridge before. This needs to be ensured in the safe client, but as this is a safety relevant system, these assurances can be made. The advantage of this proposal is that in the bridges and in the non-safety relevant clients, there is either no measure to be taken or only QM monitoring to be done. So what we do is for all safety relevant links leading to any safe client, we send those 12 sets of timestamps to a validator client that you see here on the bottom in the middle. And this validator client can now go ahead and compare for each link and for the overall system the consistency of the timing information. So in summary, what I've proposed to you is a central time validation concept that allows for monitoring done in QM. If we have boundary clock bridges, it requires additional interfaces to read the synchronized time in addition to the local time. It keeps safety load local to where it's actually needed. And yes, we do need an additional communication channel besides the PTP protocol. This can also be transferred to other bus systems like CAN or FlexRay. And there is still elements to be determined by the system designer, the frequency of these validation messages, meaning how fast do I need to detect a problem? What is the limit that I want to be able to detect? So there is things to be defined by the system designer. We can actually check with the system the consistency of the local clocks as well as the synchronized clocks. We can detect at least one of the Byzantine failures that we've looked at in the bridge. And this obviously works perfectly with the avenue holdover concept where bridges are supposed to continue sending time information if their input becomes unavailable, and they continue sending out the information to the ports, and we will know exactly by way of our additional communication channel which of these links have failed, and we know it in one safety relevant element. I want to give special thanks to Carl, who is still at BMW, to Florian and Emily at Axida. All of these have helped discussing this very patiently. They've all contributed improvements, and specifically Emily has done a lot of simulating to make sure this is not just a fancy idea, but it actually works. And if you want to do further reading, I can point you to Valentin Heider's thesis that he has written under Carl's supervision on this topic. And with that, I want to thank you very much for your attention, and I'm looking forward to the question and answer session. Thank you.